So next question is, how else can we measure fault movement and make predictions? Before we go any further though, let's do the code word for today's presentation. Now the code word for today's presentation is going to be silly putty. I repeat, silly putty. Alright, so how else can we measure fault movement? Well, we can measure it using lasers. So we can see when a fault is essentially beginning, well, we can see when the ground, should I say, is beginning to warp and deform due to a build-up of elastic stress. So that's also going to help us. Now, one of the other things which is extremely helpful is historic data. So here we go. Here's an area of California. So you've got Parkfield here. Okay, so Parkfield is near Los Angeles. And so what we can see here is we have a build-up. So all of these are the earthquakes. All right, and we can see obviously we have some rather large earthquakes right here. Okay, so what can we do? Well, what we can do is, if we have historic data, we can use that to try and predict when an earthquake should occur. So what we have here is we have a line, and this shows us the dates on which earthquakes occurred, and we also have, so we have the predicted date and the actual date. Now this line is obviously, as I say, based on the actual data because we have that in our historic record. Now the thing you'll notice is there's actually quite a reasonably nice gap between this data. Okay, so the gap is going to be somewhere, the gap here is about 12 years. The gap here is about 21 years. The gap here is also about 20 years. And the gap here is going to be, 20-something years. So, as you can see, the Parkland fault typically has an earthquake, give or take, about every 20 years or so. Now, there was quite a large gap between 1934 and 1966, so obviously that's going to be a 32-year gap. So there's a big gap there, but it gives us some idea of when we can expect an earthquake to occur. So using this data, we can essentially use it to predict the likely timing of an earthquake in the Parkfield area. Now, this was actually incorrect. The earthquake itself occurred up here in 2004, so it was late. So unfortunately, the predicted date was slightly wrong. But nevertheless, this kind of prediction using using historical data has, on the whole, actually proven to be relatively good in terms of broadly predicting when an earthquake should occur. Now, one of the other things we can do is quite long-range earthquake forecasting. Now, in this instance, we're doing it by looking at the earthquakes themselves, where they're happening. So this is essentially for the San Andreas fault between San Francisco and Parkfield, which we just discussed a minute ago. Now, faults are split up into segments. So each segment is being monitored independently here. And so what we're doing is we're counting the numbers of earthquakes which are occurring in each segment. So here you can see we have the San Francisco gap. Okay, not going to try and pronounce that gap. And here we have the Parkfield gap. Now you'll notice for the gaps in between, you have quite heavy earthquake data. Okay, there's lots and lots of these black dots. So that's telling you these are areas which are quite active. Now, these areas though, the San Francisco gap, the can't pronounce it gap, and the Parkfield gap, they have a much lower density of these black dots, which tells us, of course, these areas are much less active when it comes to earthquakes. And so this is telling us that stresses are building up because the stresses aren't being released in the form of earthquakes. So these are essentially marking out our areas of risk. Now, this gap here was sorted out in 1989 when there was an earthquake, which essentially helps to release the stresses in the area, and you can see that earthquake essentially picked out by all of these black dots. Over here we have the Parkfield gap. That was filled in 2004, as we just discussed on that previous graph. Now the earthquake itself was a bit late, but it did happen eventually. So our final gap over here is the San Francisco gap, and at present nothing has happened there. So it's probable that the next major fault movement will be in the San Francisco gap area, and chances are it will sit and have a very serious effect on the city of San Francisco. Okay, so the final thing that earthquakes are very, very useful for is interpreting the structure of the Earth's interior. So you're thinking, well, hold on a minute, how does that work? Well, it's actually quite interesting and relatively straightforward, actually. Okay, so here's our earthquake, and we have seismic waves that go into the Earth. Now, we've already shown that seismic waves can travel over huge distances, and the seismic waves that will travel those huge distances will be P waves and S waves. Now remember, surface waves will affect the local area, and then slowly they will dissipate and be lost. So a seismic wave will radiate in all directions from the hypocenter of an earthquake. Now what happens is as a seismic wave comes through, a couple of things can happen. If it comes to a boundary, and a boundary just simply means the change from one layer of rock to another, for instance, a couple of things can happen. That seismic wave can be reflected back towards the surface, or it can be refracted as it crosses over the boundary. So refraction simply says that the angle at which the seismic wave is moving will change. And of course this is a reflection of the properties of this layer of rock versus this layer of rock. So if we have a situation where we're moving from a fast rock to a slow rock, fast just simply means the seismic wave can pass through it quickly. Slow means the seismic wave will pass through it more slowly. So as we go from a fast rock to a slow rock, we will see that the angle at which the seismic wave is moving becomes steeper. If we're doing the reverse, we're going from a slow rock here to a fast rock, we will see the angle of the seismic wave become shallower. Remember, the seismic wave should just continue like that, straight down. But of course, because we've crossed from one layer of rock to another, we've changed the physical properties of the rock, and so that's refracted the seismic wave. Obviously, the same thing happens if we're going up. So if we have a seismic wave coming from a fast material down here to a slow material here, we are once again going to see that refraction. So refraction happens as the seismic wave goes down into the Earth, but also as it returns. Now, this change in angle becomes quite important to geologists. Another thing we need to take into account is we need to take into account the increase in velocity. So if we look here, we're looking at P waves. Now remember, in this instance, we've got to look at P waves because if we're looking at the Earth's interior, we know two things. The asthenosphere is liquid, and so is the outer core. So S waves are not going to do well with either of those two layers. So when it comes to looking at the Earth's interior, our primary weapon is going to be the P wave. So what do we see happening? Well, we see up here in the upper layers of the Earth's interior, we can see it gets a little bit complicated. These are different layers. So we have obviously the lower piece of mantle rock attached to the crust, of course our lithosphere, we have the asthenosphere, we have several changes in mineralogy as well, which are going to affect the physical properties of the layer, and that means that the P wave velocity up here in the top bit gets a bit choppy. Now then as the P wave enters the mantle proper, we see the P wave velocity begin to increase. Now remember, that's simply because of pressure. So the pressure is putting the minerals here under, under great pressure, and it's essentially producing minerals in which the atoms are quite close together. So we're getting denser and denser rocks. Now obviously a P wave can move faster and faster the denser a layer of rock becomes. So our P wave is going to pick up velocity as it moves down through the mantle, and then as it hits that core mantle boundary, it's going to suddenly lose velocity because it's going from a solid to a liquid. then it's going to go for our outer core, then it's going to pass its way through the inner core, and then it's going to come back out on the other side and eventually go to a monitoring station somewhere else. So this increase in P wave velocity is just related to essentially denser and denser rocks. So, excuse me, if we look at our diagram here, what can we see? Well, we're going to have our earthquake right here at the North Pole, and it's going to send waves into the Earth's interior. Now you can see these waves here are taking the path which we expect. Okay, so they're going where we expect them to go, and they're arriving when we expect them to. So what's going to happen though for these waves that come straight down, they're going to go from the fast rocks of the mantle to the slower velocity rocks of the outer core. So they're going from a solid mantle to a liquid outer core. So when these waves hit this solid outer core, of course they are going to refract. So they're going to become steeper. So the waves are going to hit the core mantle boundary, they're going to steepen up, and then it's going to go straight down. And then when they come out to the other side, you're now going to go from slow to fast. So the waves are going to become shallower when they exit, and they're going to spread out again, and we're going to detect our waves down here. Now this means there's a region from here to here in which P waves are not detected, and that's due to the refraction right here. Okay, this is referred to as the P wave shadow. In terms of S waves, because the outer core is liquid, well, if any S wave tries to cross the core, the inner core, or the mantle down here, it doesn't matter, because the S wave has disappeared here at the liquid outer core. It's gone. So from 103 to 103 over here, this is the S wave shadow. So there are no S waves in this area. So yeah, we just discussed the S wave shadow, so we don't really need to worry about that. The fact that the S wave shadow even appears tells us that the outer core must be liquid. It makes sense, doesn't it? So if the outer core is liquid, well, that means the S wave can take any of these paths perfectly happily, and we can detect it. However, as soon as it hits the liquid outer core, that's it for the S wave, and so that means we can't detect it anywhere between 103 degrees over here and 103 degrees over here. And that's our S wave shadow. And that's simply telling us two things. Number one, the outer layer of the core is liquid, and number two, it also helps us to work out the diameter of the core. So of course then we have our P wave shadow, and of course that's the result of refraction. We've already discussed this. As these waves are forced to become steeper, these waves should in theory continue down here. If the core wasn't there, they would come down here, continue this way, and we would eventually detect them right there. But we don't, because as the wave comes down, it becomes steeper, and so as the wave passes straight through the core, it means there's going to be a shadow here, so the P wave shadow here and here. In this area, no P waves are detected. So, okay. So we have these P waves and S waves, and they're allowing us to crudely visualize what's happening in the Earth's interior. So for instance, we know things like the Earth's mantle must be solid, and it's getting denser as it goes further down. We can see that in the change in velocity of the P waves. We know the outer core must be liquid, and we know the inner core must be solid. Okay, now let's go back for a second. How do we know the inner core must be solid? Well, as geologists, we can calculate how long it should take a wave to go from here to here. If we assume that the mantle is the way we model it, and we assume the core is liquid, completely liquid, we know how long it takes the wave to get from here to here. We can literally time it. However, when our waves were traveling along, we suddenly realized they were actually arriving a little bit too early. So the question is, well, how do we explain that? Well, we explain that by having a solid inner core. So that means as our P wave comes through the core, it will transition from the outer core to the solid inner core, at which point the P wave will start to pick up speed again. So this increase in speed can then be detected down here by the fact that the wave arrives early, and this instantly tells us there has to be a solid body in the center of the core. So how can we investigate deep processes in the Earth? Well, we can study rocks with a deep origin. The problem is those rocks don't tend to be that deep. They tend to be, deep crustal. But if you're trying to study things which are happening, far, far, far deeper in the Earth, unfortunately they're not going to do as much good. We can do computer modeling, and computer modeling is a very, very powerful tool, and we're actually going to discuss that more in just a second. And the other way we can work out what's happening in the Earth's interior is in the lab. Okay, so these are piston rams, and what's going to happen is a small rock sample is going to be placed here, or well, it depends on the model actually, could be down here actually, and essentially what's going to happen is this sample is going to be squished by the pistons, top and bottom. At the same time, the sample will be heated up by something called a thermocouple. Okay, so the sample will be under pressure and it will be under high temperatures, and so we'll see what happens to the rocks under those temperatures. Do they become denser? Do they become lighter? Do they expand, contract? Etc. etc. Where do the minerals change? For instance, we can model all of this using these, for instance, piston cylinder rams and other methods. There are other different types of ram which are far better for deeper and deeper, for greater and greater depths inside the Earth's interior. So the next thing we can do is what's referred to as seismic tomography, and this one is extremely interesting. So here are two earthquakes, A and B. Now we have to have at least 2 data points to make this work. So the seismic waves from A, when they're unhindered, they just go up here, up here, up there. Same for seismic waves from B, up here, follow that one. There's nothing hindering their path. So we know where they should go, and we know how long they should take to arrive. Now that's relatively straightforward. Now the thing is for instance, this wave here, as it travels along, it's transitioning from the sedimentary rocks here to a granite here. So as the wave hits the granite, number one, as you can see, it refracts. Okay, it refracts going in, and it refracts coming out. But also, it's the seismic wave is going to pick up speed as it goes from the clastic sedimentary rock here and hits the really solid rock of the granite. It's going to start picking up velocity. So our seismic wave is going to start accelerating as it passes through the granite, and as it exits the granite, it's going to slow down again. Now this means that our seismic wave will have done 2 things. Number one, it will have changed the position of the path it takes due to refraction. So the wave is going to end up all the way over here, when in reality, if it just followed the straight path of the rest, it would have come up here, and it would have probably finished somewhere around here, give or take a little bit. Okay, so this refraction and the increase in speed of the waves tells us that there's some kind of feature right here, and it's going to produce a map something like this. Okay, so we can see we've got a fast material right here and an average material around it. In this case, the sedimentary rocks is the average material and the granite is the fast material. So we know this because the waves are getting refracted, and we can see the waves arriving slightly early. So we know that essentially they must be accelerating in here. So we know that there's something fast there, like an igneous rock. So we can use it. So here we go. So this is an example of P wave velocity. So this is the Tonga Trench. So what can we see? Well, to begin with, we can obviously see the subducting piece of oceanic crust quite clearly there in blue. But we can also see the magma being produced by this oceanic crust. So remember, 150 kilometers is the magic number, okay, for magma production from subducting oceanic crust. And we can see in this area here, we have a large amount of activity going on. So these orange and red colors essentially represent areas which are slow. that means the areas are going to be liquid or semi-liquid. So these are the areas where magma is being made. And so what we can see is as the oceanic crust subducts down, it is triggering melting of the mantle and essentially the mantle rocks just below the crust. And so what can we see? Well, we can see that we have some magma coming this way. That feeds the volcanoes of Fiji. But the vast majority of the magma is coming this way. Some of it going to the Tongan Arc, which is right here. And some of it will essentially go to the Laos Spreading Center, which is located right here. Okay, and that's going to force this piece of crust this way, and this piece of crust, and this piece of crust that way, as this spreading takes place here. But you can see the power of this just by using this technique. We can visualize areas of the crust which are solid, areas of the crust which are less solid, areas of the crust which are liquid. And so this means that we can essentially model the interior of the Earth. So these are seismic velocities from the lowermost mantle, and you see them you can see they are varying from place to place. So we can see the velocities in red are slow, and the velocities in blue are fast. So slow is of course going to mean liquid, and blue is going to mean solid, if you had to take a guess. And so what we have here is a situation where, well, let's nip to this diagram here. We have a situation where we have liquid, so mantle plumes being produced. So this red area here is an area where we probably have melted or partially melted mantle rocks. And these are that's going to be the source for magma for things like mantle plumes. In contrast, we have these slightly colder areas in blue, and these are probably going to be areas which have been affected by processes like subduction. So you have a cold piece of oceanic crust coming in, and that's going to help to cool down this region of the Earth's interior. So we can see we have red areas which are essentially going to be magma, and therefore they're going to be slow in terms of how quickly a seismic wave can move through them. And then we have the blue areas here which are going to be solid, and therefore the seismic wave can move through them more quickly. So yeah, just by using this technique we can model essentially what's happening in the interior of the Earth. Okay, so that's it, ladies and gentlemen. So if you remember, the code word for this lecture is silly putty. So that's it. So don't forget to take the code word quiz, and have a good day.